In this video, we start with proving what's called the intermediate value theorem. And it simply states that if f is a continuous function and k is any number between a and b, then there must be some value c in the domain so that f is equal to k at that point. Let me draw a picture to kind of sketch what we're talking about. So we've got some domain a to b and maybe a graph that looks like this. And so we see that up here, this is f of a. And down here, maybe this is where f of b is. And what the intermediate value theorem says, let k be any number. So I just pick any number in between. So let's say this is y equals k. Then, and I just extend that line, y equals k. Then there's got to be some number in the domain c so that if I map it into that f of c is equal to k. That's all this is saying. And you're more than likely saying to yourself, well, that is quite obvious. I can look at the picture and see, yes, there's going to be at least one place where the function evaluated is k, if it's continuous, because they don't have any jumps, they don't have any holes. Just because something is obvious doesn't mean it's true. There are lots of counterexamples of things that seem obvious that are not true in all cases. And so how do we go about solving this formally? How do we use mathematics to show that just because a function is continuous, then any value in its range between f of a and f of b has to have something in the domain that gets mapped to it? Kind of like some sense of an inverse function. Well, our approach will be using an infinite number of intervals. We're going to take this interval from a to b and slice it up into an infinite number of intervals. Now, if you haven't watched the previous video in this series, I'd say go back and watch it so that you know exactly what an infinite integer is and what an infinite partition is. But I'm going to assume you've seen that video or read it in the textbook. So let's partition a to b into h intervals. And their lengths, delta, the length of each interval, will be b minus a over h. That's how long each of my intervals will be. And so we can write down exactly what we have. That, scoot this over, that we will have intervals of this form that look like a to a plus delta to a plus 2 delta, and so on and so forth. And as we discussed in the last one, the very last interval will look like this. Okay, so we've divided this into an infinite number of intervals, or an infinite number of partitions. Well, what does that do good for me? Well, notice what we know, that k is not equal to f of a. So we know that if I evaluate the function here, it's not equal to k. Now, it's possible that when I evaluate the function at the endpoint here, I'm less than or equal to k. So I can do this test going through. Let's just test, is the function equal to k, or is it less than k here, yes or no? Go to the next interval. Is it less than k, yes or no? Eventually, because I know all the way at the end point, I'm going to have a value f of b that's less than k. So somewhere in this process, there must be a k, let's call it an m. There must be an m, so we're going to look at the mth partition, so that f of a plus delta m is bigger than k, but when I look at the right endpoint of that same interval, that this is smaller than or equal. So the right endpoint would be delta plus 1 m. So somewhere there's a place, and let's do our zoom in game. So if I zoom into here, right, I can look at the interval, and at one endpoint here, I have a plus delta m, and at this other endpoint here, I have a plus delta plus 1 m. Right, so I'm looking at this interval here, and then I can ask, okay, well, where does this endpoint go and where does that endpoint go? Well, that endpoint, if I zoomed out, so if I zoom out here, so I'm going to apply my microscope to this spot here, I would have, well, the graph looks something like this. I still have this dashed line here. And I know that at this point here, y is equal to f of a plus delta m. And down here, I have that y is equal to f of a plus delta plus 1 m. Right? And this line is y equals k. Right? So I found some sub-interval, this one in particular, from a plus delta m up to a plus delta plus 1m. So this subinterval, so that the left endpoint is bigger than k, but the right endpoint is less than or possibly equal to k. Well, okay, what does that mean? Well, let's just do a little bit of math here. We have that f of a plus delta m is bigger than k, is bigger than or equal to f of a plus delta plus 1 m. Now I can take standard parts all the way across here. So the standard part of this value has got to be bigger than or equal to the standard part of k, and it's got to be equal to the standard part of this guy. So the standard part of f of a plus delta m is bigger than, when I take standard parts, I could get pushed up to equality, so I've got to add that in, k, because the standard part of k is k, and this is bigger or equal to the standard part of f of a plus delta plus 1 m. Going a little bit further, the standard parts move through, so f, well, let's just look at this, that the standard parts of these guys are k, right? The standard part here is bigger than or equal to this, standard part of this, but since this is a, these guys are infinite close, since a plus delta m is infinitely close to a plus delta plus 1 times m. Since they're infinitely close and f is continuous, we have that the standard part of f of a plus delta m equals the standard part of f of a plus delta plus 1m. Remember, that's one of our definitions of continuity, that if the inputs are infinitely close, then their outputs are equal. The standard parts of their outputs are equal, I should say. And now we put these two together, this fact and this fact, and that so the right and left endpoint are equal. One is bigger than or equal to k, the other is less than or equal to k. So this tells us that k is equal to the standard part of f of a plus delta m, which, because it's continuous, the standard part moves through. So this is f of the standard part of a plus delta m. And we'll call this value here, we'll call this c. It's some real number, and we'll call it c, so this is equal to f of c. So back to our graph, that means c is likely somewhere in between these numbers. It could be actually the right endpoint here, but still the standard part of these two values will be c, and that c is what gets mapped to k. Okay, that was a nice proof. It used infinite partitions. If you watched the previous video, you might have said, why do I care? Well, here's one reason why. It's used to prove something that seems quite obvious, though we needed to use some infinite information. We had to do this infinite cutting up of the domain, and this is going to be a common theme in many of the ideas that come ahead. So I'd recommend, just to kind of get a sense of what happened here, of maybe rewinding and watching this a couple of times to make sure that you have some sense of what an infinite partition is and how we can work with them. But nonetheless, we now have the intermediate value theorem. We know this is true. We've proven it, so it doesn't matter what the function looked like. It could be as wiggly or crazy in here as we like. What it says that as long as it's continuous and k is in between f of a and f of b, then there's some input that will get mapped to that value k. So how is this useful? Well, we've actually been using this idea quite a bit. Let's look at this problem. Let's show that the function f of x equals the square root of x plus 1 over x squared minus x squared has at least 1, 0 in the interval 1 to 2. So what does this say? Well, first off, is f continuous? Yeah, on this domain, the square root function is defined. On this domain, 1 over x squared is always defined, and then x squared is always defined. So this is a continuous function on this interval 1 to 2. Now, if I evaluate f of 1 is equal to 1 plus 1 minus 1, which is 1, and f of 2 is equal to root 2 plus 1/4 minus 4, which is less than 0. That's going to be the key fact. This is some number, but if you evaluate, right, root 2 is a little bit less than, or between, it's definitely less than 2. Add a fourth to it, this thing is still less than 2, and then I subtract 4, we're going to be negative. So the key thing here is that this is bigger than 0, this is less than 0. So we have that f of 1 is bigger than 0, bigger than f of 2. And so 0 is a number in between the endpoints. It's in between f of 1 and f of 2, so, and f is continuous. So by the intermediate value theorem, there is at least one c, a c in between 1 and 2, so that f of c is equal to 0. We didn't have to find it. We just, by the nature of this being a continuous function, that one endpoint was positive, the other endpoint was negative, then the only way that can happen is it passes across the x-axis. It has to go through 0 at least once. The theorem doesn't tell us how many times. It also doesn't tell us how to find it. That's quite a bit more work of actually finding the location of that 0. But, for instance, if we're just sketching a graph, if we know that it's positive on one side and negative on the other, then when we sketch the graph, we know it's going to have to go through the x-axis at least once.